All right, so this is kind of a combination of the rest of 6.3 and 6.4 here. So at this point, we've graphed exponential functions, things like 2 to the x that you see in that first box there. And we kind of know what a log is at this point. But what we want to look at is how are the graphs of an exponential and a log connected? And then once we figure out how to graph a log, we're going to look at some transformations, both for exponentials and log functions. So lots of graphing we're looking at today. So the first thing we want to do in this exploration here is we want to fill in these tables. So for 2 to the x, so this first table here, we've made a table like this before. So if my x value is -2, that's asking me what is 2 to the -2? Well, I know 2 to the second is 4, and I know a negative exponent gives me the reciprocal, so that would be 1/4. Okay, so and so on. So 2 to the -1 is then -1/2, or I'm sorry, 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 to the second is 4. So what we want to think about then is how on earth do we use this to fill in a table for a log? So for a log, it's actually backwards. Normally we pick the x values and fill in the y's from there. But if I were to pick the x values, log base 2, now some values I could fill in there and that would be pretty straightforward to figure out. But if I did like log base 2 of 3, that's something that's going to be a decimal, so something that's not very easy to figure out. So it's actually easier to pick the y values. Okay, so that's what this table has filled in for us. Now, something else we need to think about. We looked at inverses last chapter, and we know that a function and their inverse have flip-flop points. So, for example, if I have the point 1, 2 on a function, its inverse has the point 2, 1. So the points flip-flop, and that's true for every single point on those inverse functions. So what we're going to do when we graph these log functions, instead of first making the table for the log, we're going to first make it for the exponential function, just like we did here. And from there, then, the points flip-flop. So if 2 to the x had the point -2 1/4, log base 2 of x, notice these 2's match, so that makes them inverse functions here, has the flip-flop point. So my x and my y have flipped. And that's true for all of them. So when we graph these by hand, we're going to first make the table for the exponential and then flip-flop the points to get us the table for the log. Okay, so we're going to think about this for another exponential on the next one here, and then we'll kind of graph this one and look at some of the properties of these functions. So same idea, but my base isn't 2 anymore. My base is 10. So 10 to the -2 is going to be 1 over 10 squared, so 1 over 100. 10 to the -1 is 1 over 10. Anything to the 0 power is 1. 10 to the first is 10. And 10 to the second is 100. So now if I want to do log base 10, so the inverse function, my points are just going to flip-flop. So I've already done all the math here. I'm just filling in the points reversed. So x, y flips to be y, x. All right, so let's kind of graph these and take a look here. So I'm going to count by probably 2's here. So I won't worry about graphing that 100, but I do want to get that 10 in. So I'm going to count by 1 on the x-axis and 2 on the y-axis. So when I'm graphing this first one here, so I have the points -2, 1 over 100, so really, really close to the x-axis, -1, -1/10, 0, 1, and 1, 2, 4, 6, 8, 10. So that's that normal exponential shape we're used to seeing. And I also want to fill in, I know I'm never going to get 0 or a negative, so I have that asymptote. All right, I want to do the same thing now for my other function, my log base 10 of x. So for this one, my x values are all positives. Let's start over here. So let's see, my x values get pretty big. So I'm going to count by 2 on the x-axis and just by 1 on the y-axis. So now my x value is 1 over 100. So super, super tiny, and I have a y of -2. And then when my x is 1/10, I have a y of -1. I also have the 0.10, so that would be there. And then I have the 0.101. So notice I kind of have this shape going on. And what happens, because these are reciprocals, or inverses, inverses, I know they're going to kind of flip. So if an exponential has a horizontal asymptote, a logarithmic function has a vertical asymptote. So they've kind of flipped here. So remember, they flip over the line y equals x, inverse functions do, and we'll see a picture of that here in just a second. Okay, so I've got kind of the basic exponential and log functions here. All right, so we're going to do this part here. So they're asking for the graphs that we just did to determine domain, range, x-intercept, and asymptote of the graph. So let's do it specific to the green graph we have here. So my domain, thinking about my x values, if I have that vertical asymptote at 0, I'm never going to have an x value lower than 0. So I'm saying x is greater than 0. For my range, now this function is going down forever and up forever. Even though it's going up really slowly, it's still going up. So my range is all real numbers. And what else did they want? The x-intercept. So here, your x-intercept is going to happen when your y is 1. So we're thinking about this table on the graph, or this point on our table, excuse me. So this corresponds directly to this one. So this top one is saying, when my exponent is 0, now no matter what my base is, that's always going to be 1. So I know I'm always going to have on a log function then the 0.10. So my x-intercept is always going to be at 1. Okay? That's because on the exponential, I'm always going to have the 0.01. So this means on the log, I'm always going to have the 0.10. Alright, so that's kind of all I wanted to look at on that one. Let's keep looking down here. We're going to next go to page 167. So these are kind of the parent functions that we just looked at. So this is saying in general. So we have kind of 2 here based on if we're looking at exponential growth or decay, and that depends on what the base is. So notice the bases match up there. So b to the x and log base b to the x. So this first one is happening when b is greater than 1. And the second one is happening when b is between 0 and 1. And we've talked about that means I either have growth or decay. So this first graph here is something that we saw with our 10 to the x and log base 10 to the x. So notice they flip-flop over the line y equals x, so that's the dashed line they have there. I'm also going to draw in the asymptote for the exponential and then the asymptote for the log function. Okay, so those are also things that flip-flop, which makes sense because they're inverses. Notice that exponential, even though we don't know what the base is, it has the 0.01, meaning the logarithm has the 0.10. Similar idea when we're looking at a base being between 0 and 1. So for decay, same idea. My asymptotes are still in the same place. So the exponential has this asymptote. The logarithm has this asymptote. They're just going opposite directions. That's all. So same idea here. All right. So we are next going to go to the next page here to some of the extra practice. And I want to go to the bottom of page 168 then, numbers 17 and 18. Okay, so we're going to graph some log functions. So before we do some with transformations, because these have transformations on them, I want to do some basic log functions first. So I actually want to change this. I want to get rid of that +1. So it's just log base 2 of x. So if you were given this problem, we want to know, how do I graph this? So normally when we're graphing, we make a table. So this is no different. But the first table I'm going to make is for the inverse. So if the base of my log is 2, I'm going to have 2 to the x. So now I'm filling in our usual x values. And then I'm going to look at these different exponents then. So 2 to the -2 is 1/4, 1/2, 1, 2, and 4. Okay, so that's not the table I'm graphing, but that's going to get me my log function. So now the table for x and log base 2 of x is just going to be everything flip-flop. So I now have the point 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2. Okay, so we're first going to make that exponential table, not to graph it, but to give us those points for the logarithmic graph. Okay, so then let's go ahead and graph that. So I've got the point 1/4, -2, so really close to the y-axis. 1/2, -1, 1, 0, 2, 1, and 4, 2. So you can see it's going up kind of slowly to the right here, but it starts to go down really sharply as I go to the left. And I'm going to have an asymptote on my y-axis. Okay, so we graph the function, and they say to determine the asymptote of the function. So my asymptote here it's a vertical line, is going to be the form x equals, and this is just at 0. So we look at transformations, that asymptote's really going to help us graph as well. All right, so I'm also going to change this one here. So I'm going to get rid of the transformation. So we just have log base 1/2 of x, and we're going to start that the same way. So first thing I want to do is look at a table for my base to the power of x. So here my base is 1/2. So I'm going to do the table for 1/2 to the x. So I'm looking at my normal x values, and then I'm plugging in. So let's see, 1/2 to the -2 is going to be 4. 1/2 to the -1 is 2. 1, 1/2, and 1/4. Okay, so I'm not going to graph that one, but that's now going to give me the table for log base 1/2 of x. So because those bases match up. And now I'm just switching the points. Okay, so now we can go ahead and plot those. So I've got point 4, -2, 2, -1, 1, 0. So notice they both have the point 1, 0 here. 1/2, 1, and 1/4, 2. So at first I have a really rapid decline, and then it kind of slowly starts to, doesn't really level off because it still declines forever, but it just starts to do it really slowly. And then my asymptote is here again. So my asymptote is at x equals 0